Tag and good morning, good afternoon in Taiwan, guten Tag in Germany. And today is really my great pleasure to have Robin Novitz. Not Robin Novitz, it's Robin and Chemnitz from Free University of Berlin. And today he will share us his recent publication in science journals about the sensitivity in chemical reaction network. And we know this kind of problem are very important in applied math, and we are very interested about his approach and also this topology network structure. So let's welcome him.
Thank you. So yeah, thank you, Jayan, for giving me the opportunity to talk here about my work and giving me the opportunity to also see you again after some time ago in Berlin.
Yes.
So my talk will be about sensitivity in chemical reaction networks in relation to the network structure. And this will be a very abstract approach. So this will be maybe rather far from the application in the end, but rather shows like a nice possible approach to study sensitivity of steady states in a very general setting. And maybe for that I will give a little like almost childish toy example. Imagine this would be like some highway network. So maybe these dots are like either cities or like points where highways meet. And in between there's the roads. And within this road network you have a restaurant. And this I marked with this little hut. And you would like to have a lot of customers in your restaurant. So you would like to have a lot of cars passing by. And now you have the opportunity to fortify one of the roads. You can like make one road more frequently used, and with the goal of adding more customers to your restaurant. So a very easy thing that you could do is just like say, well, we make like these parts of the road stronger, because then if there's like cars coming from this direction, let's say, they're more likely, let's say, to pass your restaurant. So this would be a very, the most simple thing. Let's say you're in the city and you can like either make one of these connections stronger. Well, you would choose this one because that redirects people to your restaurant. But let's say you can only make a choice down here. And you can either choose that more cars are going this way, or you can choose cars are going this way. Now it becomes very unclear which of these would result in more people visiting your restaurant in the end. And this is actually the type of problem that I will be addressing today. We have some kind of network structure, we have some kind of flow through the network, and we can make small changes to the network in one place and want to learn what like responses does this cause on the other side. And we have like very intuitive understandings of what this should do. But that doesn't mean that it's easy to capture this in a mathematical way. So this is maybe the motivating picture to have in mind what we can do with this approach from today.
And Robin, and do you allow to remove the whole road? Remove this whole?
No. So today it will only be about infinitesimal changes.
I see.
So we only consider derivatives. What if I like start adding something on one node? How does it?
And do you have a loop?
We will get to that.
Okay, good.
Okay, so now the motivation for this talk itself is the sensitivity of equilibria and chemical reaction networks. So the question, when we increase the speed of one reaction very slightly, so we don't add any reactions, we don't take any reactions away, we don't do, I think there was a term for this, like if like you like kill one reaction entirely. This is not what we'll do. We'll just like perhaps add a catalyst, slightly add a little bit of a catalyst and make the reaction go faster. How does the equilibrium change? And the more general question, which was maybe motivated by the roadmap with a restaurant, is how does network structure influence sensitivity of steady states in general, in arbitrary dynamical systems, without saying what the dynamical system is. And this is, of course, a too general question to be answered in that sense, but this is like more of the abstract approach that we will take. So the outline is, I'll start with a little bit of graph theory. This will be necessary to define all the quantities in later parts, but will not be essential for the talk. Then a motivating example is the network flow. This will be closely to this cars on the road. Then I will define the most abstract version of sensitivity that I could come up with, that is the prototypical linear response. And only then we will apply all of these things to chemical reaction networks and see really how powerful this prototypical linear response really is. So this might be very basic graph theory for a lot of you. So we consider graphs which we denote by vertices v and edges e. And this is mainly important here about like which letters I will be using for what. So vertices will be small u and small v, and edges will be h. Edges are often denoted by e, but we will need e for unit vectors later, so h it is. And there's two ways to write that I will write edges. Either I will write them as with an arrow from a source node u to a target node v, or just like in brackets that it's uv, which means it's the edge from u to v. And we only consider simple directed graphs without self-loops. Simple just means that edges only connect one node to one other node, and between any two nodes there can be only one edge. So I mean, this will be important later for chemical reaction networks, because chemical reaction networks, their network structure is not simple. They're not represented by a simple graph yet. Directed, well, we already had it in the definition more or less. Going an edge in one way is not the same as going an edge in the other way. So you can have it that between two nodes u and v, you have an edge in one direction, but the edge in the other direction is not there, or it can be also there and be a separate edge. And lastly, no self-loops just means that nodes cannot be connected to themselves with an edge. And given such a simple directed graph without self-loops, we can assign weights to this graph. And that just means getting a function w, which assigns to each edge a positive number usually. And we either write this with like wuv or wh. And one last comment that will be useful later is if we have like a pair uv such that the edge from u to v it's not an edge in the graph, we can still write h from u to v, and if it is a weighted graph, we will just say it has weight 0. So that it's not forbidden to name this object, to talk about this object, just because it's not an edge in the graph, but it will just have weight 0. The next concept we'll need in graphs are rooted trees. These are maybe a bit less common. These are also sometimes called arborescences or anti-arborescences, depending on the direction. And given a directed graph, we can define or consider a subgraph with a root v0. And we call the subgraph a tree rooted in v0 if on the one hand it's a tree if you consider it as an undirected graph, and all edges are oriented towards v0. So this would be an example of a rooted tree in v0. All the nodes, in theory, not all nodes have to be part of it. In this case, all the nodes are part of it. And as you can see, if you like follow the tree along, I can actually point. You follow the tree along the edges, you will always end up in v0. So this is a tree rooted in v0. And if all the nodes are part of the tree, then we call it a rooted spanning tree. Then if we assign weights to this graph, we can define on the one hand the focus or the weight of the tree. That would just be the product over all the edge weights. Notice that it's not the sum, it's the product This will be very important for determinants later. And then we can also define the total focus of the graph, where we just sum over all rooted spanning trees. So first we sum over all possible roots, then we sum over all spanning trees rooted in that root, and then sum over the focus. And this we call the total focus of G, and denoted with this norm A. These quantities we will not use explicitly. We will never use the definition of them. It is just they will come up in the formulas, and then you know this is some quantity that you can determine in a weighted graph. We will never actually use these like spanning trees or so. So we can just think of this A, it's some quantity about the graph that can be computed, perhaps not efficiently, but it can be characterized qualitatively quite well. And the last thing about the graph theory, the last concept of graph theory that we will know, that we will need, are divided tree pairs. And given a graph, we can fix two vertices and define a divided tree pair, which I denote by TW1, TW2. And these two T's should be both trees rooted in their respective root node. So TW1 is a tree rooted in W1 and TW2 is a tree rooted in W2. Then the second line means that the trees together are spanning, so every node is in one of the trees. They're disjoint, but every node is in exactly one of the two trees. So if a pair TW1, TW2 satisfies the first two descriptions, then it's a divided tree pair. And with an additional assumption, we can, or with additional condition, we can say what a H divided tree pair is. So H is an edge in the graph. We call TW1, TW2 an H divided tree pair, or HDTP, if this edge H connects the two trees. So I write this as like TW1 and TW2 and the edge H is weakly connected, so it like forms an entire connected graph. And the observation that we can make is that in this case, when we have an H divided tree pair, there are two cases. U and V are the two nodes of H. So H is the edge from U to V. And either the edge is directed from TW1 to TW2. In that case, U, the source node, is in TW1 and the target node is in TW2, or the other way around, that the edge goes from TW2 to TW1. And to distinguish this in formula, I'll use this Boolean notation with the square brackets, where I put like a Boolean term in here, and this is just 0 or 1, depending on whether this condition is satisfied or not. The way that we will use this, this definition of divided tree pairs is, again, it will come up in formulas. And given an H divided tree pair, this term U and TW1 in square brackets is just like a Boolean expression telling us in which way are these trees divided by H. Okay, this should be enough for the graph theory. As I said, the graph theory will not actually be essential. So if there's like some things you missed now, that is okay. They will only come up in the formulas, and I don't want to include quantities in my formulas which I've never explained. So let us get back to the cars. And I call this type of dynamic the network flow. We consider a simple directed graph without self-loops, and we have positive weights. So this would be an example. The nodes are A, B, C, D, E, and with these little numbers, I've denoted the weights of each of the directed edges. Note that here between B and D, we have like in different direction, different weights. And we can define a dynamic on this network. We have some starting mass, which is a vector, assigns to each of the nodes a positive or non-negative mass. I will, like always, write my vectors and so on and matrices with the dimensionality of the vertices. So this is like a vector in size of the number of vertices. The order can be determined however you like. And here I wrote down like an example. In the node A, the derivative would be like we have an outflow of the node A with rate 2, and we have an inflow with from C into 1. And this we can define for every node. This will be a linear system, and it is defined by the so-called Laplacian. And here you can see that in the first row we exactly have the differential equation for A. On the diagonals we have all the exit rates. So for example in B we have an exit rate of 5 because there's like an edge going out with weight 2 and an edge going out with weight 3. So we have a total outgoing weight of 5. And let's consider, for example, this 3 here, which is from D to B. From D to B we have a rate of 5. And note that the edge from D to B is in the matrix LBD. So we have like, it's flipped. So this may be confusing at some point, that the weight from D to B is in the position LBD. So there will always be, I mean, this will, we do this because then we can do multiplication from the right, which is more common. And then there's, I mean, this is 100-year-old mathematics. There's nothing fancy here. If G is strongly connected, so from any node you can reach any other node, then there's a unique positive vector called the stationary distribution. These stationary distribution or equilibria I will always denote with a mu. And this is an equilibrium of this dynamical system, and it sums to 1. Okay, why am I showing you this? This is all like incredibly basic on the one hand, and on the other hand far from where we want to go. Because here in this simple setup we can already study how sensitivity works in a general setting. And that is, we consider the same graph with the same matrix, but now we choose some edge and add a little epsilon to it. So in this case I fixed the edge from D to B, and I've added a little epsilon here in the rate from D to B, which also means that the escape rate from D increases by an epsilon as well, or since it's minus, I have to take minus epsilon here. Since this graph is still strongly connected, there is still a stationary distribution, which we can denote by mu epsilon. And then the sensitivity of this is, we can just take the derivative of the stationary distribution with respect to epsilon in epsilon 0. So we have a vector delta h, so the h corresponds to the edge which we did perturb, which gives for each vertex like a value how much this value changes when we perturb this h edge. And this is exactly what I motivated with the cars and the restaurant. Imagine the restaurant is one of the nodes, and you can now have certain roads which you can fortify, which you can increase. Then when increasing a road h, this quantity exactly tells you how much the flow through this network changes in each of the nodes. So now you can just check all the roads and find, okay, is making this road larger good for me or is it bad for me? And later we will even have I mean at the moment this depends on like this is a fixed quantity, this depends on the rate in the network. Later we will even find a characterization which doesn't take the actual weights into account, but only the graph structure itself, only this graph without the weights, and can still tell you which roads would lead to a positive or a negative change. Okay, now we want to abstract this. I mean, this is a very simple setting. And the thing that I would like you to think about for a moment is that this is a linear system with a conserved quantity. Like the total mass in the system always stays the same. We have a conserved quantity. So actually one can also imagine this as the probability distribution of a Markov chain. If you know this, then you will be happy and see that this is the same. If you don't know, then don't worry. Because if you imagine this as a Markov chain, we're going to do something absolutely forbidden now. And that is, what if one of these weights would be negative? This would correspond to negative transition probability rates. And that would be, the stochastician is running out of the room now. But that is exactly what we'll do now. We'll do the same thing, but we will allow for negative weights. So we consider a directed graph, but this time the weights are allowed to be non-zero. And we construct this matrix L, this Laplacian, exactly as before. From the entry uv will be the weight from v to u. This was this flip that I was talking about before. For any of our edges, every other non-diagonal entry will be 0, and the diagonal entries will just be the entire outflow. So this we sum over the column and subtract all the entries. So this matrix will have columns summing to 0, and we have this first bullet point here so that the sparsity structure of the network, of the matrix, exactly corresponds to the graph structure. So this is just, the network flow before is just a special case of this. And as before, we can now define an equilibrium equation. So we are again looking for a vector mu, such that this mu is in the kernel, right kernel of this L, and it sums to 1. So in the network flow setting, this mu is exactly the stationary distribution, and we had a theorem that tells us this mu exists and it's unique. But now, if we allow for non-negative weights, I mean, you can find very simple examples such that this horribly fails. In general, neither existence nor uniqueness of this mu is given anymore. And even if it does exist, it's not necessarily positive anymore. It could be negative. But there is still some hope. There's things that we can do that allow for this mu to be existing and to be unique. And that is that we can make some observation about this equilibrium equation. Because actually these are not two conditions, actually this is just one condition. Because on the left-hand side we have a linear system with n equations, where n is the number of vertices. And on the right side, we also have another linear constraint on mu. You can imagine the right side as like multiplying mu by a vector of only ones and wanting that the result is 1. So actually what we could do is we could add a row of ones on top of L or anywhere in L and just require that that entry is 1. So you could write this as one matrix. But then there's even more that we can do. Actually, when mu satisfies the left equation in every but one row, then it also already satisfies it in the last row, because the columns of L sum to 0. So if we satisfy all the linear constraints, or all but one, then we already get the last one for free. So we can actually replace any row of this L by a row of ones, and then consider the linear equation where we multiply mu with this L with one row replaced by ones and require that in that row we get a 1 and in all the rest we get 0. And this mu solves the equilibrium equation if and only if we solve this matrix equation now. And this is a square matrix. So of course there's a solution that is unique if and only if this LV is invertible. And it turns out that if one of these LVs is invertible, then all of them are invertible, and it's invertible if and only if the total focus of the graph, where the graph we consider is the graph we introduced in the beginning with non-zero weights. So this is the total focus with non-zero weights. If this total focus is not zero, then this LV is invertible for any vertex. And in particular, if that's the case, then this equilibrium exists and it is unique. So as long as we don't make our graphs too crazy that the total focus is zero, as long as we don't make them degenerate, we can still define this, what I call now generalized Laplacian L, and find an equilibrium, and this equilibrium will be unique. And then we can proceed just as before. We fix an edge and we perturb it a little, which means that we increase the weight by some epsilon. And as before, we define the perturbed matrix. How does the matrix change? Well, we change the weight from U to V by plus epsilon. So this E, large E here, is the matrix which has just only one 1 and the rest is 0. And this 1 lies in the position VU. So this VU corresponds to the weight of UV. There's this flip again. And since the columns need to sum to 0 and we change the outgoing weight by plus epsilon, we need to subtract the diagonal entry in U. One important thing, that we can do this for any pair UV. UV does not have to be an edge yet. I mean, the matrix doesn't care. Like if H from U to V is not an edge yet, then we add an epsilon to 0. Imagine the edge was there, but it just had weight 0. Well, then we can still increase the weight by epsilon, or decrease the leaving rate by epsilon. So this HUV doesn't have to be an edge yet. If it's not an edge, then we imagine there is an edge, and now this edge has weight 0, and we can perturb the weight. And since we only do infinitesimal changes, the total focus is continuous in epsilon. So if it was non-zero before, it's still 0 for sufficiently small epsilon, and we still have an equilibrium, mu epsilon. And as before, we can define the sensitivity of this equilibrium when perturbing an edge H as a vector delta H, just as before. And for any target node U prime, this delta H U prime is exactly the response in one node U prime when perturbing the edge H. So delta H is the vector, and delta H U prime will be the entries. Will be the entries of this. And now we finally have our first theorem, our first equation. And it's going to look very big and daunting, but let me walk you through it a little bit. This is a formula for computing these responses in a target node when perturbing an H edge. And there's a long term, but all of the terms make some amount of sense. On the one hand, we can imagine this equation as like, we can compute it. We can describe it in terms of the graph structure. There's H divided 3 pairs coming in there, fine. But if we want to look into the formula, then on the beginning we have a factor of mu u. So this means u is the source node of the edge we are perturbing. That means if there's very little mass in the edge that we are perturbing from, then the response in general will be low, which intuitively makes sense. If you make a change somewhere where there's very little mass, you will get very little response. Then the total focus is more or less just a normalizing quantity. And over this double sum here, we're summing over all h-divided tree pairs, where one of the root nodes will be always the target node we're interested in, and we sum over all other v primes. In the back, we have like the focus, the combined focus of this divided tree pair. So this is just some math, how important these trees are. And then we have this -1 to this Boolean term. Remember, this was 0 or 1. So this just tells you whether this term is positive or negative. So actually what we do here is we have some normalizing factor in the front, and then we sum over all h-divided tree pairs, and these h-divided tree pairs either contribute positively or negatively, depending on how they are in relation to the edge h. And I will now switch to writing, so that, I mean, I will not prove this entire thing. I don't want to go like deep into the graph theory as I promised, but I want to give like a little bit of, show a little bit how one starts with something like this. So let me remind that we perturb the edge from h from u to v, and we define the generalized Laplacian in relation to epsilon as L plus an epsilon in the coordinate vu, and we subtract an epsilon on the diagonal of u. And the equilibrium equation reads, this was, I fixed some v star in v. I replaced this row of v star by a bunch of zeros, by a bunch of ones, and actually we do this to the perturbed Laplacian times the epsilon equals ev. This was this if and only if condition for the equilibrium equation, so we can rewrite the equilibrium equation in that way. And now let us look at how does this matrix actually look like. So we start with the matrix L. Then the first thing we do is we find the vertices u and v, and in vu we add an epsilon, and in uu we subtract an epsilon. And then what we do is we find this v star and replace everything by a row of ones. So this is this matrix L epsilon v star. And what you can notice is that if we choose v star to be u, then we replace this row here. Oh, I don't think you can see where I'm pointing. We replace the u row by the row of 1, so this minus epsilon actually vanishes. So we get that L epsilon u now looks like this. So then the equilibrium equation reads I mean, actually, we can now write this as just like only the matrix U with a row, the row U replaced by ones, and we get an epsilon in VU. So the equilibrium equation reads that, so this up here, if I insert this definition for L epsilon U, we get this. And actually, if we multiply mu epsilon times this matrix, which has only one, then this is exactly mu epsilon U in the position EV, and this should be EV, and we can take this EV over. So we get this equation. And now we can do the implicit function theorem. So let us define an F. Which takes an epsilon and some x, some vector x. And we exactly replicate this equation. Then mu epsilon, this equilibrium, is the solution to f of epsilon mu epsilon equal to 0. So we can do apply the implicit function theorem, and we get that this term, which is the sensitivity we're interested in, is minus the x derivative of f in the equilibrium minus 1 times the epsilon derivative in the equilibrium. So this is just the implicit function theorem. And now let us insert these terms. So if I differentiate here with respect to x, then we get minus L U to the minus 1 times, and with respect to epsilon, we get mu U EV. So since this was defined as delta H, we arrive at delta H is minus mu U L U to the minus 1 EV. And this we will need for later. So this is like how you can use this L use, replacing like one row with a row of ones, and use the implicit function theorem. And from this equation in the end, you could now proceed with like something like Cramer's rule and get determinants, and once you're at the determinants, well, then the graph theory kicks in. Okay, let me switch back. So this is how you can start proving a theorem like this. So let's get back to, I mean, now we computed this for this prototypical linear response to sensitivity. And now we can get back to the network flow. I mean, the network flow was just a special case of this, of these generalized Laplacians. So the sensitivity is in that case just a special case. This delta H that we define for the network flow is exactly described by this formula. But the difference is that now, since the weights are all positive, and we know that the equilibrium, the stationary distribution, is positive, this mu is positive, the total focus is positive, and the focuses of the t's are also positive. So actually we just sum over like a whole bunch of positive quantities, with the only difference that some of these are have a positive term and some of these have a negative term. So now we can define the sign of the sensitivity, which is that we forget what the weights are. We only care about the network structure. And now we are interested, are there weights that make this thing positive? Are there weights that make this quantity negative? And we say that the sign is positive, that no matter what weights we choose, this will always be positive. We say that it has a negative sign if no matter what weights we choose, it will always be negative. 0 if it's always 0. And we say that the sign is undetermined if there are weights which make it positive, or there are weights that make it negative, or weights that make it 0, then we say it's undetermined. So this would really tell us that certain perturbing certain edges will always have a good, or will have a positive or a negative influence on the equilibrium in certain target nodes. This is particularly interesting if you don't always have all the data of the network. Sometimes you can just like vaguely see the network structure but not know what all the rates are. Well, something like this can still tell you where you should look to achieve certain changes. And since here we just like sum over different terms, actually the sign is purely determined by the question whether there is an H divided tree pair which has a positive or a negative factor. Because if there is a positive factor, we can just choose all the edges inside these trees, make them extremely large, so they will overrule all other terms. If there is one which has a negative sign, we can make these large and overrule all other terms. So the sign is purely determined by the question whether there are H divided tree pairs, such that this term is either positive or negative.
Robin, there's a typo, right? U belongs to TU prime. U doesn't belong to TU prime in the end of the question.
This is, yeah, maybe it's written a bit suggesting the wrong thing. So is there an H divided tree pair such that U is in U prime, question mark? Then we would at least have a positive sign, or at least have a negative sign. And if there is one such that U is in U TU prime,
Okay.
not in TU prime. Yeah, so
Okay, thank you.
it's like more, is there one such that U is in there, or respectively, is there one such that U is not in there?
I see. Thank you.
But thanks for interrupting. I also want to mention again that if you care about Markov chains, this is just tells you exactly how the stationary distribution of a Markov chain changes. I mean, I just call it network floats now to not kick out the audience that doesn't know what, like, that hasn't worked with Markov chains. Keep it more dynamical. But if you have a Markov chain on a continuous time Markov chain on a finite graph, then this tells you exactly how the sign sensitivity is in that case. And right, actually, I wanted to say that after this theorem, because this is actually the theorem that tells you how the sensitivity is. So if you have a target node U prime and you perturb some edge from U to V, then we can exactly determine what the sign is for each of these nodes. And that is, are there paths from U, so the source node of H, to U prime that contain the target node of the edge V? So basically, is this path spanning the edge H? If that is the case, then we have a positive influence. If that is for any path, then the sign will be positive. If no path spans this edge, then basically this edge is pointing away from the target U prime, and we get a negative influence. And if there are paths that both span this edge H and paths which don't span this edge H, then there's an indeterminate sign. In particular, the source node will always have a negative influence because no path from U to itself contains V, I mean, because the path is empty, whereas the sign of the target node will always be positive because, well, any path to V will contain V. And here's a little example. And we will just like consider one edge. Let's say we consider this edge 8 from D to F. Then we can look in this graph here. So this is the response. And we consider perturbing the edge 8. And these are then all the signs of the responses. And we can see from A to D, they're all negative. So in this part of the graph, we'll have a negative response, which intuitively makes sense because whenever we are in D and we go to F, we'll go to E, we'll go back to D. So there's like this little cycle here on the side, which is self-contained, and increasing the rate of 8 will just like means that we spend more time in this cycle and less time in this part of the graph. Then F will be positive because, well, it's the target node. We saw that this is always positive, but it always also means that we spend more time in this cycle. The interesting thing is now in node E. In node E, it's actually indeterminate. And that is because whether you spend like more time in this cycle or more time in this part of the graph, well, E is part of both. Now the question is it better to spend more time here in the right side will lead to having more time in E, or will spending more time on the left side result in more time in E? That will depend on the rates of the network, but all the other nodes, the sign of the response is only determined by the graph structure. Okay, so this much for the network flows. Now we will finally get to the chemical reaction networks. And I consider general chemical reaction networks. We have a set of reactants and we have a set of reactions. I denote these by M and R. R for reactions, M for metabolites. We initially did this for metabolic networks. And reactions are in general of the form some amount of inputs result to some amount of outputs. So these MJs should be positive. But there can be like autocatalytic reactions in general, so an M could be on the left-hand side and on the right-hand side. Then we define the stoichiometric matrix. So the columns correspond to the individual reactions. So for example, reaction 2. Reaction 2 is A reacts to B. So we have a minus A plus 1B. The reaction 3 takes an A and a B and results in a C. So we have minus an A and B and plus 1 in the C. So this stoichiometric matrix just captures the nature of all these reactions. Then we define some dynamics on this. We have a non-negative vector x, which contains all the concentrations. Concentrations here are not to be understood as values between 0 and 1. So these are unitless. They're just like how much is there. And we have potentially non-linear reaction rates. So we don't have any particular kinetic. We don't have mass action. We don't have Michaelis-Menten or so. We just have general non-linear reaction rates. And I can summarize these as a vector. So the input is all the concentration of the metabolites or of the reactants, and the output is the reaction rates. And then the differential equation governing the concentrations of this system is exactly S times, so what happens when the reactions happen and how fast do the reactions happen. So this is a purely deterministic model for chemical reaction networks. By the way, for this introduction, I'm following the introduction of Bernhard Fiedler and Mochizuki. And an equilibrium is just an amount of concentrations such that this, SR is 0, so this is an equilibrium of the differential equation. And in general, I do not go into detail here about under which conditions do equilibriums exist, when are they unique. We'll just like assume for now we have an equilibrium given, and this equilibrium should have some non-degeneracy condition, which we'll get to later. One thing I would like to add about the reaction rates is that we can't just choose arbitrary reaction rates. We can't just choose arbitrary functions here. They should have like a certain, they should satisfy a certain condition, and that is that they only depend on their inputs. So the reaction rate of J, so I denote reactions by J and reactants by M. So the reaction J should only depend on a metabolite M if M is an input of J. And we can write this differential of the reaction rates with respect to the concentrations as a matrix R. So this is just how the reactions change, the reaction speed changes when I change the concentrations. And note that this R also has some intrinsic sparsity structure given by this, that we only have non-negative entries if there's an input to this reaction. So this R and this S both capture some network structure about the chemical reaction networks in their sparsity structure. So in the information which entries are zeros and which are not. And now we can consider the sensitivity. So we fix a reaction and we do a perturbation. We increase the reaction speed of that reaction by some epsilon, assuming that there is still an equilibrium in the vicinity. There is a condition later that will guarantee that this is the case. We can define this new perturbed equilibrium, x star epsilon, and as before we can determine the sensitivity of this. And unfortunately, I think for time reasons, I will not do the computation on paper. If you do this,
you may have 10 minutes. Okay.
Yeah, that will be fine. So this degeneracy condition is that this matrix SR is non-zero, and if that is the case, then the sensitivity is given by minus SR minus 1 and then Sj. Sj is the jth column, so this is the stoichiometric representation of the reaction J. Also, the reason why I skipped this is none of my work. This is in these works by Fiedler and Mochizuki. I have a reference in the end. So this is where they developed this kind of approach and also found this degeneracy condition and made this computation. It's again an application of the implicit function theorem. So now let's get to the main part that I have announced in the beginning. We want to use this prototypical linear response to compute sensitivity in chemical reaction networks. And here is like maybe a little bit summarize why this might be surprising that this is possible. On the one hand, the prototypical linear response, as the name says, it's linear, while the chemical reaction network is by itself the reaction rate as a dynamic nonlinear. Then in the prototypical linear response, we had a simple graph structure. All the edges were just like directed edges from a U to a V. In chemical reaction networks, we have a complex graph structure. We have hyper edges. So, for example, a reaction from A and B to C is like one complex edge. So we don't have like a very simple graph structure. Also, one of the characteristics of the prototypical linear response is that we have a conserved quantity. Remember, this mu had to sum to 1. In chemical reaction networks, when changing the speed of the reactions, the total mass in the system might stay the same. Also, we might have feed reactions. I denoted this by 0, 2, A, for example, this means just like we put in A from outside, or we have exit reactions where chemicals vanish into energy or some output, and then we don't see them in the system anymore. So there's no conserved quantity. So these are all like points which we have to overcome in order to apply this prototypical linear response to chemical reaction networks. We can start doing some tricks. We've seen here that this matrix SR is kind of like at the core of this sensitivity. We have this equation which determines this is the sensitivity of the chemical reaction network. So all we need to do is find a linear, a generalized Laplacian, a prototypical linear response which inhibits exactly this as its own response, and then we're done because we have a formula for that. And the matrix that we construct is the following. The vertices, or like the dimensions, is all the metabolites, and I add the zero, which is like the zero complex, so no chemicals. I add it as an extra node, and I add this extra node here in the beginning. So the first row and first column corresponds to the zero, and down here we have m cross m. And here in the top row, I just added a row such that all the columns sum to zero. That way it is a generalized Laplacian. It is a matrix whose columns sum to zero. So this is a matrix. We don't know the graph structure yet. We all have to figure that out later. But for now, this is a generalized Laplacian. And the determinant, remember that like generalized Laplacians were allowed if we replace one row by a row of ones, then the determinant should be non-zero. And if we replace the zeroth row by a row of ones, then the determinant will just be exactly SR. So we have a unique equilibrium, and this equilibrium is given by the unit vector in 0, because if I multiply here E0, then I just like get this column at 0. So this is the unique equilibrium. So we can study the sensitivity of this mu, which is E0. Now we computed here, remember this equation. So when perturbing a edge from U to V, the response is given by this equation. And now we do this for an edge from 0 to m. Note that this edge might not be part of the network, but we said that is okay. Then we just increase the weight of from 0 to epsilon, and I just insert this equation. Mu 0 is 1. Then we get this inverse of L0, which I computed up here. And we multiply with the unit vector of the target node, that is m. So we have this first line here. Since mu is just the unit vector in 0, this is just a 1, so we can omit this. And note that this matrix has SR minus 1 in the lower left corner. So if we multiply by an m, which is a metabolite, then we just get exactly these entries of SR minus 1 down here. So if we restrict this vector, which is in m and 0, to just the metabolites m, then we exactly get minus SR minus 1 times EM. So all that remains is that we need to sum up a few of these to exactly reproduce this sensitivity of the chemical reaction network. And that is that we sum over all the inputs and outputs of this reaction J. And then we have these responses of the prototypical linear response in here. So this gives us a formula for describing the linear response or the response of a chemical reaction network in terms of prototypical linear responses of this matrix L. The only thing that remains is what is the graph structure of this L? Because that is really the interesting part. I mean, before we determined the sensitivity of the prototypical linear response in terms of its graph structure. So what is the graph structure of this L? Remember, L has like SR in the bottom right. So here I have this simple chemical reaction network in the beginning. Here the matrices S and R, and down here we have the matrix SR. And then the top row, just make them sum to 0. So here we have in total minus RC. So here we have RC. This R2B and this R2B, 2 minus 1 plus R2B. So in total we have an R2B at the top. So these just make them sum to 0. So wherever we have a non-zero entry, we will get an edge. So there's a few things that make edges. If there is a reaction from A to B, for example, then we will get a reaction also in the influence graph, an influence from A to B. A has an influence on B. But now B will also have an influence on A. And that is because when there's more B, then this reaction 2 will happen faster. So B will have a negative influence on A. And this we can actually see here. Unfortunately, I didn't put the labels on anymore, but the influence of B to A is in this entry. So if B increases, then this has a negative influence on A, and the influence is exactly the reaction rate of reaction 2, or the derivative of reaction rate 2 with respect to B. So if B increases, then reaction 2 happens faster, so more A is consumed, so B has a negative influence on A. And that means that in this influence graph, there's also an edge with negative weight from B to A. Also, all the reactions that consume quantity or increase quantity will have edges to 0. Because in total we need to have like conserved quantity, and that is why we include the 0, because then like basically the 0 is our bin where we can either draw mass from or give mass to. And then this is the final result. What we can apply these formulas, and we get, as before. I don't want to go too deeply into these formulas. It's just you can do that. We have constructed a graph now, and we can determine the sensitivity when perturbing a reaction J in a target reactant M prime in terms of the graph structure of this influence graph. Here we have an A to the 0. I didn't introduce this before. For our purposes at the moment, this is exactly the actually exactly the total focus. So just the 0 could be omitted. I realize now. And again, we sum over all divided tree pairs. This time we're not summing over H divided tree pairs because J itself is not an edge, so we can't sum over H divided or J divided tree pairs. But instead we just sum over all divided tree pairs that there are and determine whether they influence the thing positively or negatively based on whether in this reaction the metabolite is they're like whether they're consumed or produced in this reaction. And this determines whether these the weight or the focus of this divided tree pair will play in positively or negatively. And one last nice corollary of this is that if we have a monomolecular network, or we perturb a monomolecular reaction, so just a reaction from some M to an N, nothing else, then this term in the middle just has like one positive, 1 plus 1 and 1 minus 1. So actually we get a term just as before. So this entire equation is more or less exactly the same as this linear response in the network flow setting. So this, maybe, Jayan, you remember this from my talk a while back ago on my master's thesis. This corollary was basically what I have stumbled upon there, that the response in monomolecular networks is actually just a response of a Markov chain or a network flow. And as it turns out, one can actually like extend this with like slight modifications to general chemical reaction networks, and this is this top theorem. So everything that I've been talking about today in this talk is in this paper, which has recently been released in SciAm of Applied Math. And these references of Mochizuki and Fiedler, which are like introducing this chemical reaction networks in a very nice way, and their sensitivity are these two papers, which I've basically just like been more or less copying for the small introduction. Thank you.
Thank you very much, Robin. Thank you very much for this very nice talk. And yeah, I think there are so many interesting structures, and so maybe some audience have some question, comments, or remarks. Yes. Maybe let me start. Okay. So in the end of your, can you go back to your slide one page back? Yes. So here the equilibrium is not necessarily positive, right? You are.
I mean, these are for the chemical reaction networks, and the chemical reaction networks, the equilibria, they should always be positive.
Be positive. Yeah. So can you also go back a little bit and yes, this influence graph. Can you remind me again, how did you get an influence graph? Add one H and so are these two networks? You have a chemical reaction network and also the influence graph. Are they related? They are related, right?
Yes. So just based on the stoichiometric matrix,
yes,
you can determine the influence graph. And it is true, I did brush over this a little bit briefly, because the time was running out. But there's like a few like rules which determine whether there is an edge in the influence graph. And the first thing is, if there is like a reaction such that two metabolites are in the same reaction, then there will be an influence. They will have an influence on one another. Mm-hmm. So for example, here in like A to B, then A and B will be part of the same reaction, so A has an influence on B.
Yes.
But if in the reaction A and B go to C, then A and B will both have an influence on one another and on C.
Yes.
So if there is, for every reaction that a reactant is part of, they will have influence on all other nodes. I mean, C will have no influence on A and B, as we see here. But A will have, since it's reaction of part of reaction 1 and reaction 2, it will have influence on B and on C. And B is part of reaction 2, so it will have an influence on all other reactants of the of this reaction 2. So it has an influence on A and it has an influence on C. Since this chemical reaction network is very compact, I mean, it's only like 3 metabolites, this will lead to a very like almost complete graph. Mm-hmm. If the network is larger and we have like really components far away from one another, so that if like 2 metabolites or 2 reactants are not they don't share any reaction, they will not get any edge in the influence graph. But of course, I mean, then we will get like an interesting graph structure. Yeah. And this graph structure will then be the graph structure of this generalized Laplacian, where we can find divided tree pairs and so on.
Okay, thank you. Yeah. Okay, some questions, comments? Yes, so let me ask you more, okay? So basically you are doing one of the application of sensitivity analysis, in my opinion, is of course to study bifurcation, right? Mm-hmm. When the implicit function theorem fails, okay? And of course, there's a spatial condition, there's a non-dimensional condition. And you have now a very good formula. Next page, okay? Now you have this very amazing formula. with this formula, can you design a simplest chemical reaction network such that some bifurcation occur? For example, transcritical bifurcation. I want a transcritical bifurcation. Maybe from your formula, you can already design a small list network, like only 3 nodes or two reactions, such that this work. Because you have this very nice formula. Yeah.
I don't necessarily think so, because we had the standing assumption that like this matrix SR is not degenerate, which basically tells us that if we make small changes to reaction rate, then there's no like qualitative change. We don't pass any
That's not bifurcation.
things that one can do with this that or like one could dream of doing with this is one thing get like a sign sensitivity for chemical reaction networks, which is still very hard.
Yes.
And it's, to my knowledge, even unclear whether it can be done like in one formula or whether it's like NP complete or so. I mean, if it's NP complete, then you will have no hope of finding a clear description. And the other thing would be that the nice thing about these about this formula is that if you perturb now two different reactions, the sensitivity will just be additive, since you have like just the derivatives. So if you like, now you could like determine will there be cancellations, because these are all basically algebraic terms in of R, of like these. I mean, all the weights are determined by the matrices S and R. So if you view these just as variables, then this is basically just a polynomial. And you can now determine under which conditions, if I perturb two reactions or more reactions at the same time with certain ratios, will some of these terms algebraically cancel?
Yes. And when they cancel, what happens?
Sorry, again?
What happens when they cancel?
Well, when they cancel, then you might be able to find very specific sensitivity patterns that, for example, you want to increase a certain reactant, but you want to not touch the equilibrium of others. Let's say we're like in drug design for like, some metabolism. Let's say you want to increase something which needs to be increased, but you don't want to mess with that like organism's vital equilibria. So then you might need like two influences at a certain ratio such that they like in general will increase the target, but the cancellation will exactly not influence certain parts of the reaction network.
I see. So this is kind of like a control problem.
Yes.
Interesting. Okay, cool. Yeah. So other questions?
Robin, thank you so much for your nice talk and very clear. And as mentioned in the beginning, you would like to study the reaction rate is fast, and come back from the inflation graph. If the reaction rate is very, very large, I mean, if the rate is very big, what is the steady state for this system?
So actually in this case, the reaction rates don't have to be large, because the terms of this in these T's, these weights are never the actual reaction rates. The actual reaction rates I denoted by a small r. And note that these nonlinear reaction rates never actually occur from this point on, because here we just like have this capital R, which are just the derivatives, so how the reaction rate changes when I change the metabolite. So when I say that we will need like very large values, very large weights in this graph, then we will need very steep changes in the reaction rates. And one way that, I mean, this is of course a very abstract approach, but in general you can, for example, using Michaelis-Menten kinetics, you can choose your parameters such that you have any given equilibrium that you want to have with any given derivatives in this equilibrium that you want, any given linearization. So in that case, the equilibrium can still be whatever we want the equilibrium to be, but we will have like just very, the equilibrium will be very sensitive.
Thank you so much.
And so my colleague, Professor Huang, remind me of a question, because he is an expert in reaction diffusion equation, okay, in population dynamics. If we discretize, then of course we also have a network structure and there's a random walk. And this random walk can be implemented in the graph, in the network structure by, there's a delta of xm, like you take a mean, okay? So what happens if you consider this random in your...
Yeah, actually I did consider this at some point.
Page, people say this is a page dynamic, PATCH, page dynamics of population, yeah.
I mean, that I am no expert on, but I can say that what I did consider is if we have, let's say, some general dynamical system in space, for example, and you partition the state space now, then you can define a Markov state model so that the partitions of the of your space will now be nodes of the network. And I mean, maybe I can actually draw this here.
Yeah, please, thank you.
I mean, this will be now a very vague picture, but let's say this is our space. And we have some type of dynamics in here. I don't know, might be a bit chaotic. Now we divide our state space into a couple of large-scale states,
Yes.
and make each of these a node. And now the idea of Markov state models is that you define like transition like probabilities between these states. So
Yes.
from this, you are very likely to go here.
Yes,
From
yes,
this state, you're probably going here. And from this,
Yes.
there's like kind of a, let's say, 50-50 chance where you're going next.
yes, yes.
One need to be a bit careful here because let's say there's also like a chance that you could go here with like, I don't know, maybe there's like the tiniest bit that would be going this way. This would mess up our graph structure. So we need to be quite like, have like a large threshold such that we consider it an edge, because otherwise we will have a lot of edges with very small rates. So let's make this network very coarse. Then we would have like basically a network representation of our
Yes.
dynamics.
Yes.
And now you can study sensitivity with this if like, I don't know,
Interesting. Yeah.
this part will happen faster.
Yeah, I see. If I remember correctly, recently I saw a paper, or I had a discussion with a guy in bioinformatics. They use this kind of viewpoint, and this kind of dynamic can be captured by a single delay differential equation. Single delay differential equation. And maybe your sensitive analysis is also can be incorporated into the delay setting. That would be interesting. Maybe I will send a paper to you if this is published. Yeah, I understand this. Wow, this is a quite a broad viewpoint, very general. I see.
I mean, yeah, maybe I stress this again, that like really this approach that, I mean, I've been talking about chemical reaction networks only for like the last 15 to 20 minutes.
Yeah.
And that is really because like I want to have the weight on this like very abstract nature of this prototypical linear response. And that even though chemical reaction networks inhibit a lot of properties that seem like they would be incompatible with that, you can still, by considering the linearization and creating this influence graph, make like artificially any sensitivity problem into a linear response.
I see. Yeah, good. So questions, other questions? Okay, maybe before we finish this talk, then let me ask you, because you are expert in this relation network. So what do you think? What's the future important topic of this relation network? Because you can do a lot. There's a big network. There are topology. There are ODE. There are numerics. What do you think? What are the most important direction of research?
I mean, importance is a difficult question for a mathematician.
Interesting for you.
Yes. I mean, from the work that I did, the most like interesting aspect is, on the one hand, there's still this open question about the signed sensitivity of chemical reaction networks, because that is maybe for like a chemist in the lab, everything that we will find out, they found out in practice like 30 years ago. So we will not that will maybe not help them in the lab, but it seems like a very interesting, also graph theoretic question, because you have like a very complex network structure. And I mean, what I did today was showing that like this sensitivity or sign sensitivity in simple directed graphs is rather easy. So this would be this one, like for example, I mean, my conjecture on that is actually that is NP hard or NP complete, which is that it is impossible to find such a thing, which also would say that we can stop looking for it. But I'm no expert on like this complexity theory, so I wouldn't know how to prove something like this. And the other thing is exactly this cancellation, which I believe does have also an actual application, some relevancy. Because I mean, as we said, like if you want to change certain things, but you don't want to touch a lot of things, not only if we know that they would do something bad, also sometimes we don't want to try to change something because we don't know what it does. So these would be the two things that I think are the
I see. Yeah.
next like directions that I think are interesting: cancellation and sign sensitivity of general chemical reaction networks.
Okay. Yeah. Okay. Very nice. Thank you. Yes.
Thank you.
Okay. So other question, comment, remarks, or even counter examples? Okay, if this is not the case from the audience, and let me thank our speaker, Robin Chemnitz. This time I pronounced correct. Okay, Robin Chemnitz again. Thank you.